Number 15, we need to identify the transformation, use coordinates to describe. So we have a triangle ABC, and it's going to turn into, its pre-image is ABC, its image is A prime, B prime, C prime, and we need to decide, is this a translation, a reflection, a rotation, or a dilation? So we have, we can see that this small triangle is getting larger. Well, translation is where you just move something, you slide it. So it's not that. It's not a reflection because it's not like a mirror image. We didn't rotate this triangle. We kept it the same orientation. So which means it's going to be a dilation. So we need to see, dilation is where you make something smaller or bigger. We need to see what is our scale factor. Let's measure A to C. Line segment AC is 1, 2, 3, 4 units. Line segment A prime, C prime, let's see how long that is. 1, 2, 3, 4, 5, 6. That's halfway there, so it's going to be 12 units. So our scale factor means what do we multiply by? And our scale, so what is our scale factor? Well, we multiplied from here to here by 3. So it is a dilation with scale factor of 3. Number 16, we need to decide, are these congruent, similar, or neither? Congruent means exactly the same size and shape. Well, clearly one of them is smaller than the other, so it's not congruent. Similar or neither. Now we need to decide, are they similar? Do they follow the same ratio? I can see A's width is 2. Its height is, let's see, from here we go up 1, 2, 3, 4, 5. It's 2 by 6. Then let's see, the other one is 1 wide and 1, 2, 3. So quadrilateral B is 1 by 3. So are these proportional? Is this similar? Similar would mean it's proportional. Do we have a constant rate of change between these two? Well, I can see that this is, from the big one, we cut it in half. From the big one, we cut it in half. It's always times 1/2, times 1/2. So this is another dilation. These are similar. It's a scale factor of 1/2. For number 17, we have some angles here. We need to figure out what angle C and angle B equal. We don't have an angle A in this one. So what is angle C and what is angle B? Well, I can see if we have a whole straight angle here, it's going to be a total of 180 degrees. So 73 plus 60 plus C equals 180. So you need to figure out, well, what do you need to add to those two numbers to make 180? That'll tell you what C is. And now check this out. We've got parallel lines, so whatever the angle C is, it looks like they're the same size, C and B. These are corresponding angles. We're going to talk about that next week. Corresponding angles are congruent. They're the same. They are congruent. They're the same measurement. So whatever you get for C is going to be the same thing for B. For number 18, we need to solve. Here's number 18. A cylindrical water tank is 25 feet across and 40 feet tall. So we've got a cylinder water tank. So it's like a cup. Cylinder, you know what a cylinder is. So it's 40 feet tall, and then its diameter across is 25 feet. So we want to know how much water can fit in this. Capacity means inside. How much water will fit in here? So we need to find the volume. The volume of anything, any type of prism, which a cylinder is a type of prism because it's a circle repeated over and over and over and over again all the way to the top. Same diameter all the way to the top. You find the area of its base and you multiply it by its height. So volume is base times height. Its base is a circle, so the volume here is going to be, the area of a circle is 1/2 base times height. And then we need to multiply that whole thing by the height. I want to make that a capital H because it's the height of the whole shape. So I say 1/2 base times height. That's not even close. Area of a circle, pi, area of a circle equals pi times the radius to the second power. So we need to do pi times the radius is halfway across. I know all the way across is 25. So we need to cut that in half. So that's times 12.5. To the second power means we've got to do times 12.5 again. And then we need to multiply by its height times 40. So you need to multiply all these together. You can use the pi button on your calculator. Pi times 12.5 times 12.5 times 40. You're going to get a pretty big number. Make sure you put your label as feet to the third power. For this last question, number 19, a giant sequoia tree up to 311 feet tall can weigh up to 2.7 times 10 to the 6 pounds, while a 50-foot pine tree weighs about 2.0 times 10 to the third pounds. How much more does the sequoia weigh than the pine? Here's what I want to show you. I want to show you a picture of one of these because I went and saw one of these. I saw a lot of these this past summer. This is one of the smaller ones. You couldn't get really close to the huge ones. But I did see the largest tree in the world. There's me standing next to one of the small ones. Okay, so about the width of a car, but the biggest one was more like the width of almost a whole house. It was insane. So I'm going to get rid of this though. Well, I can leave it up. I'll leave it right here. That's me standing by my sequoia tree with some other tourists. This is in California. So we want to find out how much bigger is this tree than a regular old pine tree. So let's see. 2.7 times 10 to the 6. What that is, that's times 10 means you move your decimal 1 time. So we got to move our decimal 6 times. We're multiplying this by 100,000 or a million. 10 to the 6th would be 10 times 10 times 10 times 10. It's got 6 zeros. Times 10 times 10. So we're going to move it 6 times. So we start with 2.7. We're going to go 1, 2, 3, 4, 5, 6. And I think I just went 7. 1, 2, 3, 4, 5, 6. In these empty spots, we get zeros. We have 2,700,000 feet. Not feet, pounds. We're talking about weight. Pounds. And then a regular pine tree is 2. We move it 3 times. 1, 2, 3 is 2,000. So what is 2,700,000 minus 2,000? Because we want to know how much more the sequoia weighs. Go ahead and do that subtraction. Give me the final weight of the difference between the sequoia tree and regular tree.